Hello everyone. This work focuses on unpaired image-to-image translation. Learning to translate data from one domain to another is an important problem in computer vision for its wide range of applications, such as colorization, super resolution, and image imprinting. In unsupervised settings, where only unpaired data are available, current methods mainly rely on shared latent space and the adoption of cycle consistency. In particular, by forcing the translated images to follow the discriminator using a classical adversarial loss and translating those images back to the original images, cycle consistency ensures that translated images contain enough information from the original input images. This helps to build a reasonable mapping and generate high-quality results. The main problem of cycle consistency is that it assumes the translated images contain all the information of the input images in order to reconstruct the input images. This assumption leads to the preservation of source domain features, such as the trace of glasses in part A and the beard remains on the face in part B, resulting in unrealistic results. Besides, the cycle consistency constrains shape changes of source images. For example, the hair and the shape of face are changed little in part B and C. To avoid the drawbacks of cycle consistency, we propose a novel method termed ACL-GAN, where ACL stands for adversarial consistency loss. Our goal is to maximize the information shared by the target domain and the source domain. The adversarial consistency loss encourages the generated image to include more features from the source image, from the perspective of distribution, rather than maintaining the pixel-level consistency. That's to say, the image translated back is only required to be similar to the input source image, but need not be identical to specific source image. Therefore, our generator is not required to preserve all the information from the source image, which avoids leaving artifacts in the translated image. The source image is used as a reference to guide the translated image. Besides, the input noise vector Z enables multi-modal outputs, which is essential to build the distribution. Our second contribution is bounded focus mask. Some applications require the generator to only modify certain areas of the source image and keep the rest unchanged. We adopt a tension mechanism to generate the mask, and propose two constraints to limit the size of the foreground and clarity of segmentation. Combining the adversarial consistency loss with classical adversarial loss and some additional losses makes our full objective for unpaired image-to-image translation. We analyze ACL-GAN by comparing 4 different settings. Quantitatively, we observe that our adversarial consistency loss successfully helps to preserve important features of the source image in the translated image, compared with the setting of ACL-A, which already had identity loss and bounded focus mask. For example, as the red arrows on results of ACL-A show, without adversarial consistency loss, the facial features such as skin color, skin wrinkles, and teeth are difficult to maintain, and the quantitative results are the worst. Even though it's difficult to quantitatively compare ACL-I with the others, ACL-GAN achieved better quantitative results than ACL-I. We found that ACL-GAN with bounded focus mask has better perceptual quality. For example, the background can be better maintained compared with ACL-M. The quantitative results indicate that our bounded focus mask improved the quality of images because the mask directs the generator to concentrate on essential parts for translation. We compared our ACL-GAN with baselines on 3 challenging applications: glasses removal, male-to-female translation, and selfie-to-anime translation. These 3 applications have different commonalities between the source and target domains, and they require changing areas with different sizes. The goal of glasses removal is to remove the glasses of a person in a given image. There are two difficulties in this application. First, the area outside the glasses should not be changed, which requires the generator to identify the glasses area. Second, the glasses hide some information of the face, such as eyes and eyebrows. The sunglasses in some images makes it even more difficult because the eyes are totally occluded, and the generator is expected to generate realistic and suitable eyes. Our results leave fewer traces of glasses because cycle consistency is not required. The goal of male to female translation is to generate a female face when given a male face. And these two faces should be similar except for gender. Comparing with glasses removal, this task does not require to remove objects, but there are three difficulties of this translation task. First, this task is a typical multi-modal problem because there are many possible ways to translate a male face to a female face. For example, different length of hair. Second, translating male to female realistically requires not only changing the color and texture, but also shape, such as the hair and beard. Third, the pair data is impossible to acquire. That's to say, this task can only be solved by using unpaired training data. Two results of ACL GAN show the diversity. Our results are more feminine than baselines with cycle consistency loss, and our faces have no beard, longer hair, and more feminine lips and eyes. Different from the previous two tasks, generating an animated image conditioned on a selfie requires large modification of shape. The structure and style of the selfie are changed greatly in the target domain. For example, the eyes become larger and the mouth becomes smaller. This may lead to the contortion and dislocation of the facial features. Without cycle consistency loss, our method can generate images more like an eye. For example, the size and the layout of facial features are better organized than baselines. The adversarial consistency loss helps to preserve features, such as the haircut and face rotation of the source images. Quantitatively, our method outperforms all baselines on both FID and KID. Please refer to our paper for more details.